Perfect. Okay. I don't have my tripod, so I gotta rig something up here, right? With these ice tables, setting up the ice tables is one of the most important things, right? When you're looking at an ice table question, you should be thinking to yourself, okay, when I read the question, let's read this question all together at the same time. The initial blah, 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 and equilibrium blah, 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 okay? So it says something, initial something, equilibrium something. Immediately you know for sure you're going to have to use an ice table. Why do you know for sure you're going to have to use an ice table given this question?
Because we have initial and equilibrium.
It's got initial and it's got equilibrium. I'm going to have to use an ice table. But that's okay, because you're all amazing at ice tables right now. So when we look at an ice table, the most important part is getting our balanced chemical reaction. Often on the diploma exam, they'll give you a balanced chemical reaction most of the time, but every once in a while you might have to balance it yourself. Rarely do you have to make an equation. Now yesterday, I asked you to make the equations, just because it's good to get you to think about how do I make a chemical reaction, right? How do I write one? How do I do this? That kind of thing. So in our Google Classroom, under Chapter 15 assignments, I did last night, good thing it doesn't say the time because it was very late, ice table practice and the practice key. And so the key is on there. Do you want me to go through any of these three examples, not using the key? Do you want me to just go through it from the start and just make sure we're all on the same page? Or are we happy with ice tables? Who wants me to go through one from the start?
Let's do the last one.
Yeah, let's do the last one. Sure, let's do the last one together. It's going to be pretty quick. It's actually going to be really quick, so there's no harm in doing this. Okay, it says 3 moles of carbon monoxide are reacted with 4 moles of oxygen in a 2-liter cylinder. If 2.5 moles of carbon dioxide is created at equilibrium, man, whoever wrote this isn't very good at English. That's fine. Carbon dioxide is created at equilibrium. What is the equilibrium concentration? So I know, read the first sentence. Does it say the word initial? No. But is it implying at the beginning? Yes. Okay, you have to know that that means initial, right? So we got carbon monoxide is reacting with oxygen gas. We know it's in equilibrium, so we'll use our equilibrium arrows. And it's going to make carbon dioxide gas. Now the first thing we have to do is we have to balance this chemical reaction. 1 carbon, 3 oxygens, 2 oxygens. A little trick that sometimes, I don't know if you remember this from your Science 10 or Chem 20 days, if your Science 10 or Chem 20 teacher told you this. This is almost like a combustion reaction. Would you agree? There's something with oxygen is making CO2, okay? So if your oxygens are off, right? We have 3, we only want 2. If your oxygens are off, then as long as you balanced everything other than the oxygens, double everything else. Just double it. So did we successfully balance the first and the last thing? Are they kind of equal to each other? 1 carbon and 1 carbon. Yeah, sure. So I'm going to double them. 2 carbons and 2 carbons. And then let's reassess and let's see how many oxygens we need. 2 and 4 and 4. Oh, all right, we're done. Is that okay? That's a little trick whenever there's a combustion reaction and it's the oxygens that don't work. So we've got a balanced chemical reaction now. And it says it wants us to do something, 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 initial something, 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 equilibrium. So we will put ice, ice, baby. Three moles of carbon monoxide, 4 moles of oxygen, and 2.5 moles of carbon dioxide. Now, straight out of the gate, I don't like that. I don't like what I just wrote. Does anybody know why I don't like that? Just going to give you 10 seconds. Don't say it out loud. Do we kind of know? Do we kind of know the problem associated with this? What do these numbers mean? What are the units attached to these numbers? Moles. And whenever possible, what do we want to turn it into? Moles per liter. We sure do. So instead of writing 3 moles of carbon monoxide, what should I have written? So I'll take my moles, right? 3 moles, and I'll divide it by my volume, so I get moles per liter. So this really should be, oh man, hopefully this doesn't erase more than I want it to. Whatever, doesn't matter. That looks terrible. Okay, 1.5 moles, 2 moles, and then this is going to be nope. And this is going to be 1.25 moles per liter. Good. So now everything is in moles per liter. And now I can do this really, really easily, or what I consider to be really, really easily. Are there any assumptions that we have to make in our ice table? Sky?
CO2 is at 0.
We should. It's saying we're starting with this much, and it neglects to say anything about any of the products, right? So we just assume you don't have any. Well, we know that our change must have been positive 1.25. And up here, I would always like us to put what the changes in general should be. So I'll take this value, and in order to get my x, what should I divide that by? I'll take this value and I'll divide it by 2 in order to get my x. So my x is 0.625. You take that and you divide it by 2, you get 0.625. So if I'm losing 1x, how much am I losing here? 0.625, right? 0.625. So 2 minus 0.625 is 1.375. And then if I'm losing 2 x's, well, we know 2 x's is 1.25, so 0.25. Are we okay with that?
So what I did is I just divide by 2. Is that okay?
At the end,
yes.
Right? Yeah. So we're going to find out today and, not tomorrow, Monday. We're going to find out today and Monday that it's much better to have the equilibrium values in concentrations already. Because we're going to do something today / Monday where if they're in moles, it won't work. But if they're in moles per liter, it will. Okay? So straight out of the gate, it's nice to put everything in moles per liter. That way you don't have to remember it kind of after the fact. Okay, perfect. What I want to know, this should have been, do you agree this should have been 2.00 to start with? Like if I take into account significant digits? Okay, what is 2.00 minus 0.625? Is it 1.375? No, it's not. Okay? And this goes back to our talks about significant digits. This goes back to our talks about significant digits. Now, would you all agree that when I take the number, like, in order to get 2.00, I had to take 4.00 and I divided it by 2.00, right? So my concentration in moles per liter was 4.00 moles over 2.00 liters. So 4 divided by 2 is 2, and I should have 3 significant digits, moles per liter. Is that, like, you've probably been using that rule every day in chemistry for the last, semester or whatever, right? When you took Chem 20. That's called the certainty rule. There's a certain amount of certainty in both of these numbers, and we have to round to the lowest amount of certainty. We have to round to the least certain number of digits. But 3 digits divided by 3 digits is 3 digits. Okay, sure, no problem. But think of this. I'm going to take my 2.00 and I'm going to take away 0.625. So let's do this by hand. Who knows minus 5? Do you know what that number is?
No.
No. You have no idea what that number is. Would you agree? You've got absolutely no idea. It doesn't give you a value here. What do we kind of assume it to be? 0. We assume it to 0 because there's no other option. We can't assume it to be 9. That would be ludicrous, right? So we assume it to be 0. 0 minus 5 is 5. But it's still a question mark. We don't actually know that it's 5. You've got no idea. But whatever, okay. Well, so that minus that, so blah, 9 minus 2 is 7. Blah, 9 minus 3, or 6 is 3. 2 minus 0 is 2. So no.
2.
Woo! Holy.
I was like, that doesn't work.
No, that doesn't work. Good thing that's going up on YouTube. Okay. So our answer should be 1.375. This is what we call the precision rule. You have to round to the least precise measurement. Which one of these measurements was less precise? The top one or the bottom one? Which one has less decimal places? The top one. So this 5, you don't actually know that it's a 5. But we're going to assume it's kind of a 5 and use it to round to the least number of decimal places. So there's 2 decimal places here, 3 here, so we got to round to 2 decimal places, right? Should this 7 stay as a 7? No, it should round up to an 8. And that's like an often not used, like, when was the last time you used that principle when you were doing rounding and things like that? And you, yeah, okay. So, anyways, that's why if you look on the key for this thing, the first answer is not 0.435 because it's the exact same thing, right? You don't know what that digit is, minus 5, it's a 5, but the 5's got to round the 3 up to a 4. So that's why the answer for the first one is 0.44 moles. The second one's fine. No, it's not. Sorry, it's not fine. It's the same thing. So 21.8 and then 1.38. But anyways, the key's up on Google Classroom, and we're going to move on to bigger and better things here in a second. Let me know if you want more ice table practice. I can probably whip up some more ice table practice. But for the meantime, we're going to talk about equilibrium expressions and this idea of Kc. So I don't know if you remember me kind of harping on the idea that percent reactions don't hold up across all of the concentrations, right? If I vary the concentrations a little bit of my reactants, I can actually get a totally different percent reaction. So instead of using percent reactions, we're going to use an idea called an equilibrium constant, or Kc. Or sometimes it's even called KEQ. It stands for equilibrium constant or equilibrium constant, whatever, it doesn't matter. The constant is calculated using the equilibrium expression below. So let's write an equation. I don't know, pick 4 letters. Boo. Okay, fine, whatever. Pick 4 single-digit numbers.
9, 3, 5, 6.
9, 3, 5, 6. So 9 of these reacts with 3 of these to make 5 of these and 6 of those. Are we okay with that? Just whatever, chemical reaction, doesn't really matter. So here's our chemical reaction. And I want to be very clear. The concentrations of all of these chemicals at equilibrium, not initially, but once equilibrium is established, the equilibrium concentrations are all related based on the following principle. Kc, in general, you can think about it as products over reactants. But more specifically, that's a terrible K. More specifically, the Kc is equal to each individual product raised to the power of their coefficient. Kc just stands for equilibrium constant. That's all it means. This is a constant. This is a number that will always hold for this particular chemical reaction at this specific temperature. Okay? So CD, what's the coefficient on C? 5, so it's raised to the power of 5. What's the coefficient on D? 6, so it's raised to the power of 6. And we've got A raised to the power 9, and B raised to the power 3. Now, if that confuses you, you're probably not alone. I'm gonna write this chemical reaction in a different way, okay? And I'm ruining the time that I asked you for 4 random single-digit numbers, but whatever, it doesn't really matter. I'm gonna write this reaction in a different way. How many A's are reacting together?
9.
A plus A plus A plus A plus A plus A plus A, 2, 4, 6, 7, plus A plus A. And how many B's are reacting together? 3 plus B plus B plus B gives us, is in equilibrium with, how many C's is it making? C plus C plus C plus C plus C. And how many D's are we making? 6. Oh man. Would you agree that this is the exact same thing as that? It's just that we've almost like combined our like terms. It's a math thing, right? Good? Yeah. So 9 A's are reacting with 3 B's to make 5 C's and 6 D's. Well, the idea is that we want to take the concentrations of all the products and multiply them together. Right? On top is the concentrations of all the products, and you multiply them all together. And you divide by the concentrations of all the reactants, and you multiply them all together. Well, how many A's should I have on the bottom because it's a reactant? How many A's? So I'm going to have the concentration of A times 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 the concentration of A. How many A's are here? 9. So that's A to the power 9. Does that make sense? That's where this comes from. A to the power 9 times B to the power 3. It's just all the A's and all the B's being multiplied by themselves. Are we okay with that? And then all the C's and all the D's on top. That's why the coefficients come into play like that. So note, what do square brackets mean? Concentration in moles per liter. That's why when we look at our ice tables, it's super important. It's really, really important to have these in moles per liter. Because if a question ever asks you to calculate the equilibrium constant of a reaction, you just take these values and you plug them into your equation. But if you did your ice table in moles, then you have to remember to divide by your volume and then do it. So there is a big difference between those. Okay, so let's just do an example. So we've got the reaction. 2 ammonias are turning into nitrogen gas and 3 hydrogen gases. Now, I will always try my best to give you a temperature, because when I change the temperature, I change Kc. The equilibrium constant is only good for a specific temperature. If I heat up a reaction, we'll learn this later, but if I heat up a reaction, I change the number of products and the number of reactants, and that alters our equilibrium, okay? But that's fine, that's just for later. The equilibrium concentrations at 673 Kelvin are this for those things. So what I want to do is write the equilibrium law expression. I want to be very clear. The expression is just the formula, products over reactants. That's the equation, okay? So I want to see the equation. In the second step, I want to actually physically calculate the number, Kc, the number for it. So let's write the equilibrium law expression for this reaction. In general, Kc is what? Always what on top? Products. All the products being multiplied together. How many products do we have here? 2, right? So I'm going to go the concentration of N2 gas times the concentration of H2 gas, and I'm going to divide it by my reactants, which is NH3 gas. What's the problem with this?
Units.
Nope. Not units, because we haven't put a number in yet, right? A unit is always associated with a number.
Bubble.
Yeah, I gotta have those coefficients in there, right? I need to have those coefficients. What's the coefficient on N2? 1, so I'm just gonna leave it, right? Something raised to the power of 1 doesn't matter. H2 raised to the power of 3, and NH3 raised to the power of 2. That's the expression. So if I ever ask you for an expression, that's what it means. It's like the equation. What does this look like? Now I'm asking for the actual value of the equilibrium constant. This should be pretty easy. We're just going to take our values, plug them into the equation, and see what we get. So the concentration for N2 is 1 mole per liter. So that's 1 mole per liter raised to the power 1. Concentration of hydrogen is 0.5 moles per liter raised to the power 3. And the concentration of ammonia, right, on the bottom, was 2 moles per liter raised to the power 2. So I want you to try this out. Take out your calculator. Does anybody need a calculator? Ooh, yeah. Caitlin, can you catch? Yes, you can. There you go. John, can you catch? Hey, Bogdan, this is probably coming at your head. Yeah. Anybody else? Camille, can you catch? Only time will tell. There you go. So you should get a pretty tiny number, like a relatively small number, right?
0.03. Yeah.
What did we get?
0.03125.
0.03135. 3125.
Yes.
0.03125. Now I want to make it very clear, Kc values are like pHs. We define them to have no units. Okay? A Kc value will never have units. I know you could make a set of units out of this, but it's a constant that has no units. Okay? Now I want to be very clear. Our answer is wrong, right?
Yeah.
Yeah, why is it wrong? Should only have 3 significant digits, right? So this should be 3.13
times 10 to the power of negative.
3.13 times 10 to the power negative 2, right? 3.13 times 10 to the power of negative 2. Perfect. Hey, there you go. Now, I don't want you to write anything down. I'm just gonna go back up here and we're just gonna take a very general perspective at what this is. If I said a reaction was greater than 50%, would that mean reactants are favored or would that mean products are favored? If I said a reaction went to greater than 50%, that would mean products are favored, right? Because, would you agree, if greater than 50% of this stuff turned into that, then that means we've got more products than we do reactants, right? Now we can do the exact same thing with Kc values. I'm gonna write down the concentrations up here, and you tell me if this reaction is products favored or reactants favored. NH3 was 2 moles per liter, N2 was 1 mole per liter, and H2 was 0.5 moles per liter. So does it look like, based on these concentrations, does it look like it was reactants favored or products favored?
Reactants.
Would you agree, in general, it seems like there are more reactants than products, just in general, okay? So reactants are favored, and what did we get for a Kc value? Did we get a really large Kc value, or did we get a really small Kc value? Oh, that's interesting. Curious. Okay, let's move on without talking about it again for a little bit. Let's talk about homogeneous equilibria and heterogeneous. Man, you've probably heard those terms at least 3 times before. Would you agree? Homogeneous and heterogeneous? Probably more, yeah. But I mean in 3 separate contexts. What does the prefix, right? A prefix is a word that you glue on to the beginning of another word. What does the prefix homo mean? Same. It means same. Homo sapiens is the correct genus and species term for human beings. Homo sapiens means same as us. Are we all the same species?
I don't know.
Yeah.
We could be cyborgs, one of us could be an alien. It could be
No. Let's move on without commenting on that. Okay. So a homogeneous equilibria is where all the reactants and products are the same state of matter. If a reaction is homogeneous, if they're all the same state of matter, then we will use every substance to calculate the equilibrium constant. If it's not, if it's heterogeneous, and what I mean by heterogeneous is when you look at all these states of matter, what are all of them? They're all gases. If one of them's different, then that means it's a heterogeneous reaction, and there's a separate set of rules, and we'll talk about why that is when we come to it. So, for example, write the equilibrium expression for this reaction. Well, you've already done that, right? We just did that. What was the equilibrium expression for this reaction? Kc is what? The concentration of hydrogen gas raised to the power of what? 3 times the concentration of nitrogen gas raised to the power of what? 1. So we just won't write it. All divided by the concentration of ammonia gas raised to the power of what? 2. Okay, in general, the equilibrium constant expression is always what over what? Products over reactants. Always, 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 okay? Here, let's take a look at this. I know that this is a crazy chemical reaction. I understand that, okay? But let's take a look at it and let's ask ourselves, is this homogeneous or is it heterogeneous? This is homogeneous. Would you agree all of the states of matter are the same as each other? Then it doesn't matter what they are, you have to use every single one of these terms in the equilibrium constant. Kc, specifically for this reaction, Kc is what? It's CH3, COO, CH3. Liquid. Being raised to the power of what? 1, so we don't write it. Times water, liquid, being raised to the power 1, so we don't write it. It's all divided by the concentration of methanol, liquid, raised to the power 1, so we don't write it, multiplied by the concentration of acetic acid. That. Raised to the power 1, so we don't write it. Was that very difficult? Yeah, okay. Cuckoo and cooch. I don't know, whatever. Doesn't matter. Okay, heterogeneous reactions. If a reaction is heterogeneous, we only use aqueous and gaseous states in our equilibrium constant. Is that okay? We are not allowed to use liquids, and what else are we not allowed to use? Solids. And the reason why that is if we look at a reaction, so there's a beaker, right? It's a bottle and a stopper or something like that. And we've got a liquid in here. I want to be very careful about the way I express this. Let's say there's some gaseous particles, right? And they're condensing into a liquid. So something's going from a liquid to a gas and vice versa. Okay, so we've got condensation and we've got evaporation happening in this bottle. It doesn't really matter, it doesn't really honestly matter how much liquid is in here. Because is the liquid at the bottom of the flask, is it doing anything? Is the liquid at the bottom of the flask evaporating? No, it's not doing anything. And also, if I added more water, would the concentration of the water change? No. If I added more water, the volume would get bigger, so the concentration doesn't change, okay? You can't change the concentration of liquid water if it's the only liquid present, okay? Can I change the concentration of this gas? If I added more gas molecules, could I change the concentration of the gas? Yes, because gases can be compressed, okay? So you can change the concentration of a gas. You can't really change the concentration of a liquid unless it's a reaction like this one when they're all liquids. If you pour two liquids together, they mix together and their concentrations change based on how much of one liquid there is. Okay, that's complicated, and if you didn't understand that, that's totally fine. The moral of the story is, if you have a heterogeneous reaction, you only use aqueous and gaseous entities in your equilibrium constant. So, let's take a look at this. Is this homogeneous or is it heterogeneous? This is heterogeneous. Immediately you know it's heterogeneous because I see aqueous and gas. Boom, two different things. We have to use our heterogeneous laws in order to do this. So we're still calculating Kc. Are we allowed to use the concentration of hydrogen in my Kc?
Yep.
Yes, because it's a gas. And gases, their concentrations can change, right? H2 gas raised to the power what? 1, so we don't write it. Am I allowed to use the concentration of zinc chloride? Yeah, because it's aqueous. Can you change the concentration of an aqueous substance? Yes, an aqueous substance you can. By just adding more zinc chloride, it dissolves in the water. If I add more zinc chloride to water, does the water's volume change dramatically? No, it dissolves into the water and the volume doesn't necessarily change. So the concentration of zinc chloride is not fixed. It can change. So we're allowed to use it. Zinc chloride aqueous. Raised to the power 1. On the bottom, are we allowed to use zinc?
No.
No. Because if I add a chunk of zinc, does it dissolve into the water? No, it doesn't. Remember, elements don't dissolve, right? Or they don't dissolve to any appreciable extent. So if I add more zinc, I'm just adding more chunks of metal, and that's increasing the volume of everything. But the concentration of zinc isn't changing. Does that kind of make sense? So we're not allowed to use zinc. What we will do, you don't have to do this, but we can put the number 1 as a placeholder. We can just say that its concentration is 1, and it'll never change. We're just using that as a placeholder. This equilibrium constant is just a number. It just represents the extent of the reaction.
Is it okay if I didn't put 1?
It's okay if you didn't put 1, because what happens when you divide by 1? What's going to happen? Nothing, and that's the beauty of us putting 1. Okay? It doesn't actually change the value of the constant. I have to use hydrogen chloride because it's aqueous, and what's it raised to the power of? 2. So it doesn't matter if you put the 1 there. It doesn't matter if you don't put the 1 there. The math stays the same. I want to be very clear that this can be used as a placeholder. Is that okay? Okay, because some of you, I'm going to give you another worksheet here in a little bit, and some of you are going to be hella confused by some stuff. So that's whatever. It's okay. So let's try the second one. Really quickly, it's the concentration of carbonic acid, aqueous, divided by the concentration of carbon dioxide, gas, multiplied by the concentration of water, liquid. No. No. That's wrong, isn't it?
Yes.
That's the worst thing I've ever seen in my entire life. What should I do?
Raise
Erase the water. Why erase the water?
It's liquid.
It's a liquid in a heterogeneous reaction. Good. You can use the number 1 as a placeholder if you want, right? We just define it to be 1 as because it's not going to change. It doesn't really matter what number we put in there.
What if we have a completely solid homogeneous reaction?
You can't. Not that you can't, but solids don't typically react with each other. Okay? Because solids do not have enough kinetic energy to collide and to be able to change their potential energies. Oh, is that okay? We'll talk about that later on in the energy thing. But solids typically don't have enough kinetic energy to be able to do that. So what I would like us to do is work on this homogeneous, heterogeneous reaction worksheet.
He's like, are you okay?
I apologize, they're not hole punched. There's 3 hole punches in the room.
They're not actually gonna do that.
So what I would suggest that you do, the way I would suggest you do this is, yeah, I know it says write the equilibrium expression. That's great, do that. That's kind of the main purpose of this activity. The first thing I would suggest that you do, go through the entire list of however many reactions there are, 12 or whatever, 11 reactions, and label them as homogeneous or heterogeneous first. Why does that go 1, 1? 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, there actually is 12. Whatever, it doesn't matter.
They both wanted to be number 1.
They both wanted to be number 1. That's the way it's...
That's exactly that.
So that's what I would like you to do. First label them as homogeneous or heterogeneous, and then make the Casey expression.
Which one are we in?
Yeah, het, that's fine. Het. Het.
So which one
Correct. You would divide by the number 1.
made a noise, it's like coffee and then you thought that it was so just like
Sorry.
I was like, everything's fine. Yeah, like thinking about it.
I saw you break out in laughter, and I thought if I ignore it, it would go away.
You just gotta give me time.
Yeah.
Sometimes I just stop laughing. And sometimes I don't, and it just goes on forever.
So when yeah, because if I add water to this, and I'm changing the concentration of the water, right? The water's concentration can't change unless it's Yeah, they can be ions, totally. Yeah. Nope. You labeled it homogeneous, right? Oh, right. What's the rule for homogeneous reaction?
I just stopped breathing. I haven't even had any sugar. the reactant.
The product is the outcome.
Yeah, but sometimes it's like the other way around.
No, I agree, but the way the reaction is written right now, what do you make either way? The way the reaction is written right now, you're starting with this, and then turning it. Yes, yeah. Like, it's a little bit confusing because by definition this is an equilibrium reaction. It goes both ways, right? But the way we wrote the equation, the products are always on the right side, the reactants are always on the left side. I wanna what?
Do you want this one's really
That's why I said on the.
Reactants are always on the left. Right? Reactants are always on the left, products are always on the right.
It doesn't use
No, that's the reverse direction. Reactions, like traditional reactions, always go from left to right.
It's not if this was reversed. It's even if it is reversed, it doesn't matter. It's still the reactant is the outcome. But this is the outcome.
So, yes, the things on the left are always on the bottom. The things on the left are always on the bottom.
But if this is the outcome, it's the product.
That's not the outcome, that's a reactant. We define
They're breaking it
reactants.
down.
We define reactants to be on the left. Like JC, if I said this, what's the reactant and what are the reactants or reactants and what are the products or products? C is the product. It's the same thing as here. It's always products on top, always the things on the right on top, always the things on the left on the bottom. Always, always, always. And I'll
Yeah.
that reaction is backwards.
Well, no, it's like breaking down instead of.
Okay, JC, I want you to take a look at, this is gonna sound stupid. I want you to take a look at the second number one, right? So that's just this reaction, and the reaction labeled 4. What do you notice about them?
It's the same, but it's backwards.
Exactly. So I want you to write the expression where products are on top, reactants are on the bottom, no matter the way it's being represented.
Is it always going to be like that?
Yes, always, always, always. We define it to be that.
Here, do we put the charge?
Yes, on the inside. Yeah.
Oh, wait, what is this? Oh, wait. Okay. If it's hetero, the only ones who use are ones with gas. Only gas? Yeah. And aqueous.
Yeah. Well, it's because you asked. It's stupid, okay? But only because, like, what's 5 divided by 5?
It's just like the state, it's just the charge.
Oh, 1 times.
1 divided by 1.
It's just because it's aqueous.
That's why we use the number 1. Is because what are you going to have on top? The number 1. You're going to have to go to 1. Some people want to put the number 0, right? Because they say, well, we're not allowed to use it when we put the number 0. No, we're not allowed to use it. because water can be gas. If you boil it, right? Yes, so it's gas that was made, or it's water that was made in a gaseous state. And it could eventually condense, but right now it's a gas. Good.
Is there all right there? I didn't realize like this was.
It doesn't matter, right? Yeah, exactly. And you can ignore every single, in a heterogeneous reaction, every single one you can totally ignore, with the exception of that.
Okay.
Right, you have to write it that way, or 1 over, or you could put a C on it to the power of -1 if you wanted to.
Just one.
Then
Then
there's
it's
C in that way? Yeah.
technically there's no problem.
The key is at the front. If you're done, or if you're halfway through and you want to take a peek or whatever, the key is at the front. I ask that you leave it at the front. Let me know if you have any questions. I'm going to give you 2 or 3 more minutes. Yeah, there's an answer key, but that's fine. Which one? All of them? Yeah. It's perfect. Okay, all right. It seems like you demonstrating your. No, it doesn't. It doesn't. No. But I just want you to be aware that that is a possibility. So on the diploma exam or on the unit exam or something like that, if there's a value missing, then you can assume it to be 1. Not that it's 1 mole per liter, but we're just using the number 1 as a constant.
Psych.
What?
Okay. Okay, wait, Maddie.
If it's a gas, always.
That's why we took that. Because we wanted, like, Newton and I wanted to see. That's basically the only example of a homogeneous reaction involving fluids that ever come across as that kind of reaction. We wanted to use that as a test. Are people paying attention, or are you just saying liquid? Don't use liquid. Well, you didn't. What were my instructions at the beginning? I said label everything as either homogeneous or heterogeneous, right? No, I know, but I just verbally said it. I didn't write it down. So. No, I know it's fine, but we're just trying to make sure that we catch that right away. It's good, trust me, Chelsea, it's good to make that mistake. You will never make that mistake again. Yes, sir. Again, I'm going to give you another minute or a couple minutes, and I'll toss up the piece. Yeah. Oh, it might be that exact problem. I don't know. I'm going to put the key on Google Classroom later, but yeah, take pictures all you want, right? Regardless of how far you've gone on that worksheet, can I make sure everybody attempts the very last question, please? I would like everybody to attempt the very last question in the next minute. No, I just want to use it as a litmus test. I just want to use it to see if we all are on the same page.
That's what I heard.
Yeah.
Like, I am not.
I heard
Yeah. CO. Yeah, absolutely. Carbon dioxide has to be raised to the power 2 because the 2 is a coefficient, and carbon dioxide is just 1. Awesome.
So if then the gas and whatever is on that
if it's hetero, you cannot use liquids and you cannot use solids.
So
If it's homogeneous and you have all liquids,
okay.
because liquids can mix together, and when two things mix together, their concentrations change.
So the way that I did it, I took out all the solids and liquids, so that I need to go through my homogeneous.
Exactly. Yeah. You're only allowed to take out solids and liquids if it's heterogeneous. Okay, 30 seconds to try the last one. 30 seconds to try the last one, please. Yeah, it's totally fine. It's perfectly fine. And in fact, it's third, just right here, right now. I just want to make sure we all understand that each
Homogeneous. Homogeneous.
That's the reason why we use that as a placeholder. Okay. So hopefully you had a little bit of time to try out that last question. Okay. So we're going to go through the first couple reactions. And hopefully this makes sense. Yeah, that's okay. In that first reaction, is there anything we're not allowed to put in our Casey expression?
H2O.
Yeah, H2O. So you can either leave it out or put the number 1. It's perfectly fine if you do either, as long as you're aware. For the second one, is there anything, I know it says number 1, whatever. For the second one, is there anything we're allowed to leave out? No, because it's homogeneous. Anytime you see a homogeneous reaction, you have to use every single one of them. Okay, carbon dioxide and hydrogen and carbon monoxide and water. I wanna just do the next one, but then I'm gonna come back to this. Absolutely, you are allowed to use concentrations of ions. If you're using the concentration of an ion, you have to tell me it's the ion. So you have to put positive or negative or +2 or -2 or whatever, right? But absolutely, you're totally allowed to do that. We're not allowed to use water. Why? It's a liquid in a heterogeneous reaction. Awesome. Okay, can I get everybody to focus on, this is confusing, the second number 1. Look at the second number 1. And also, at the exact same time, look at number 4. What do you notice about those two reactions? What do you notice about this reaction and number 4? They're the exact same reaction. It's just that we're expressing it in a reverse way, right? Would you agree? Carbon monoxide plus water turning into carbon dioxide and hydrogen gas is the exact opposite of carbon dioxide and hydrogen gas making carbon monoxide and water, right? It's just reversed. So, if a reaction gets reversed, what do you do with the Kc expression? Flip it. Do you agree that our products in one version become the reactants in the reverse version? Does that make sense? So because you flip the reaction, you have to flip your equilibrium expression. Does that make sense? That's going to come into play here in a little bit, okay? I'm going to put the key on Google Classroom if you want to. That's totally fine. I'm going to skip all the way to the very end. How many people made the mistake of ignoring everything for this last reaction? Okay, lots of people aren't being honest, but that's fine, whatever. As long as you understand, hey, this is homogeneous, I cannot look at the states of matter anymore. You have to use them. And the reason why that is, when I mix methanol and pure acetic acid together, their volumes combine and they mix together, and so you're changing their concentrations. Their concentrations, because it's two liquids mixed together, their concentrations are allowed to change now. So because their concentrations are allowed to change, we're not allowed to use the number 1 as a placeholder. Hopefully that makes sense. Okay. Woo! Now, there's kind of one last thing that I'd like to talk about, and then we will get into using ice tables.
Oh my god, this
The booklet hates you? Oh, okay. Well, if you put it in the binder, you can just take the staple out, right? You really want to? Whatever. Okay, you're smart. Kc is a value that communicates the relative position of an equilibrium. What that means is it quantitative? Is it reactants favored? Is it products favored? Or is there no reaction? Okay? So let's use our percent yield descriptions that don't work all the time. So a greater than 99% yield. Remember that was quantitative. Greater than 50%, less than 50%, and 0% reaction. So the term we use for greater than 99%, that was quantitative, and I'm going to run out of room. I hate that, but I will. There you go. Quantitative. If I say a reaction is quantitative, that means all of this turns into the products. Every single last little bit of it. Except for maybe the 0.000001% that doesn't. Greater than 50%, is that products favored or is that reactants favored? If a reaction, if greater than 50% of this turns into that, what do we have more of, products or reactants? Products, right? Right? If we start with 10 of this and more than 50%, let's say 6 out of the 10. If 6 turn into this and we're left with 4, right? Greater than 50% means products favored. So that means products favored. And because I don't have a lot of room, I'm just putting P favored. Hopefully you know what that means. Greater or less than 50% means reactants favored. And 0% meant there was no reaction. I'm putting no RXN again because I'm a chemist and I'm a lazy. What kind of an arrow would we use for a quantitative reaction?
Just one arrow.
Just a straight, just one arrow. That's all you need to show me that this reaction is 100% in one direction. Products and reactants favored are the equilibrium arrows, but we have to put greater than or less than 50% above it, right? Greater than 50%. Less than 50%. Sorry, it's all kind of blurring together. I apologize. Maybe I'll try and, sure. Whatever. Doesn't matter. Okay, and no reaction, we just write no arrow, right? We just typically don't use an arrow. Maybe I should put no arrow, I don't know, whatever. It'll be pretty obvious. Now, what I want to think about, let's use this example. Was this products favored or was this reactants favored?
Reactions.
At equilibrium, what's there more of? Products, right? Okay, so let's think about this. Let's assume that this was the concentrations of these two things. What would be the Kc for this reaction? Kc is the concentration of B, right, divided by concentration of A. What would that be in this case? It would be what? It's not b to the 6 or anything like. It's just 6 divided by 4. What's 6 divided by 4? 1.5. So products favored. If something is products favored, our Kc is always going to be greater than 1. Can you understand? If we had a reaction that was exactly 50%, right? What would these two numbers be? 5 and 5. What's 5 divided by 5? 1. If a reaction is 50%, that means a Kc equals 1. Another way of thinking about this, probably a more effective way of thinking about it, is in general, what is Kc always? Products over reactants. If products are favored, right, that means the top is big and the bottom is small. If you've got a big number on top and a small number on the bottom, is your Kc value going to be big or small? Big. It's going to be greater than 1, right? Right? So let's say 2 over 1. That's going to be greater than 1. Would you agree? Right? But what if reactants were favored? What if reactants were favored here? 1 over 2. Is that Kc going to be greater than 1 or less than 1? It's going to be less than 1. So this is what we're saying. If the products are favored, you can tell using the Kc value, because the Kc value will be greater than 1. If a reactants favors the reactants, or the reaction favors the reactants, your Kc will be less than 1. It'll still be positive, right? You can't get a negative Kc. That's not possible. What if there's a no reaction? If you form 0 products and everything stays as reactants? 0. 0 divided by something is 0. Or very, 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 very small, right? Now, what if 99.99999% of it turns into products and 0.000001% turns into or stays as reactants?
Approaching infinity.
Yeah, approaching infinity. Or we just say it's very large. Sometimes it's so large you cannot measure that value. It's impossible to measure a Kc. That's 1,000,000 divided by 0.0000000001, right? If you mess up by half on the bottom, your number doubles. It's impossible to be able to measure that accurately. We just say it's very large. Man, this thing reacts so much that you might as well not even think about it. Is that okay? Are we good with that? Yeah. How much stuff do you think we can squeeze into 40 seconds?
No.
I guess you can have a good weekend. I guess. I'm going to put the key and this kind of worksheet that you just did. I'm going to put it on Google Classroom here in a little bit. Somebody.